Ah, I like this comment a lot because this means this person is starting to have a keen eye to the subtleties of calculus, of convergence, of limits. So why wouldn't it be true? It seems like for the common folk, it would be obvious that 9.99999 repeating divided by 9 is just 1.11111. What is to be checked? Why is that not rigorous? Well, what is happening from here to here is that we are dividing every single digit, every 9 in that expansion by 9 to get a 1 digit. But that means that there are infinitely many 9s that I'm dividing by 9 to get a 1. And whenever we do any process that involves infinitely many steps, there is something to be checked to make sure that doing that does give me this other number. The question here comes from a video where I was trying to prove that 0.9 periodic is equal to 1, and I multiplied by 10, and then I had 9.9 periodic, and I wanted to divide by 9 to get 1.1 periodic. Let's prove instead rigorously that 9 times 1.1 periodic is equal to 9.9 periodic. So the first thing to notice is that that decimal expansion rigorously is this infinite sum. So this quantity is 9 times the infinite sum, the geometric series of 1 over 10 to the k. And the technical issue that we are dealing with here is that I want to prove that I can distribute this 9 over this sum of infinitely many terms, just multiplying by 9 every single term. But that's not how the distributive property works out of the box, because the distributive property just says that a times b plus c is a times b plus a times c, but it doesn't say anything about distributing a constant over a sum of infinitely many terms. So I have to use the definition of a sum of a series first to be able to show that I can distribute this 9 inside of this infinite sum. And that is, in fact, the sum of the infinite series, which is, by definition, a limit. It's a limit of partial sums, where the partial sums are the s sub n, that in this case are the sums from 0 up to n of the terms in the series. So in this case, 1 over 10 to the k from 0 up to n. Now, the limit of the partial sums converges because this is a geometric series. A geometric series of ratio 1 over 10, which is less than 1, so the geometric series converges. So that series does have a sum, and the sum, so the limit of the partial sums, is 1 over 1 minus r, where r is the ratio, which in this case is 1 over 10. So the sum of the infinite series is 1 over 1 minus 1 over 10. The point is that the series converges and the limit of the partial sums exists. So the geometric series converges and the limit of the partial sums exists, and it's equal to that value. And when a limit of a sequence exists, a constant times the limit of the sequence is equal to, by the properties of limits, to the limit of the constant times the elements of the sequence. In this particular case, Sn was a partial sum, and since it is a finite sum, now I can multiply 9 by every element of that sum and get this other partial sum. But this other partial sum is a partial sum for this expansion of a decimal number. So in summary, what we have proved now is that 9 times 1.1 periodic is equal to 9 times the sum of that geometric series, which is convergent. And we've proved that 9 times that series is equal to the sum of this other series, which corresponds to the expansion of 9.9 periodic, which is what we wanted to prove.